Okay. So hi everyone, I'm Thomas Garnier from Recon system, and I will talk about Alpc and the Alpc interfaces and the previous escalation on Windows. So basically, this presentation is on two different parts. The first part will be about the Alpc, the second part on the Alpc, and as it has been said, we will see the basic architecture, some explanation about an exploit that has been reported to Microsoft, a demonstration of this exploit, and talking about how we can protect Windows against this type of attacks. There is a paper that will be released in the Recon website. It will contain a lot more details about the exploitation. That should be available after the conferences. Okay, so what is the Alpc interface? Basically, the Alpc interface is a local socket system. That's a communication system across process with local features. It has been created for the Windows NT subsystem. It has been undocumented, and basically you can interact with either privileges process. The Alpc interface is its improvement in the Windows Vista. It supports the old Alpc functions, and everything has been rebuilt in order to make better performances and change the whole design. So the Alpc is interesting because many system processes export Alpc interface, a public Alpc interface. So that's a way to access privileges process. Most Windows API that deal with thread or anything related to process goes through Alpc, even if we don't see it. The transportation for some components like RPC or other is done by the Alpc. And Cesar Sirdo introduced a feature of the Alpc that allows remote mapping section. Basically, you are able to map a section on the server process, and you have the remote base address. That's made the local privilege escalation a lot easier. So that's mainly why the Alpc interface is known for privilege escalation reliability. Now the Alpc is well documented on the internet, so you don't have to reverse many things to understand how it works. The ALPC is interesting because it shares all the points of the Alpc. And of course, we can ask ourselves how it has been improved on the design and on the security part. In the security part, it has been done with the security development lifecycle. And as the Alpc interface, we will see in the next slide, the Alpc interface was not secure in the first version. So basically, we ask ourselves if the ALPC will be directly secure or it will have some security issues. So the Alpc interface works with a client, classical architecture, a server, a client. As it's local, it used a named object called a port. Basically, you create a port when you create the server. You can apply ASIA restriction on this port. And this named object is used for the connection. Incoming connection can be discarded by the server depending on information. And everything is based on a message system. When you want to ask a connection, you send a connection message. Same for disconnection, for request or reply. Everything is on the kernel through the message-based system. There is many vulnerabilities on the Alpc interfaces. Basically, there is two types of vulnerability. First, about the kernel design. As I said, the Alpc interface was not secure in the first version. So there was some design issue. You were able to sniff some message that was for another server. You were able to send a message specifying another process and another thread. And you have more typical vulnerabilities based on the way the userland interface parse the data you send through the Lpc. So those examples, there is even more vulnerabilities that just some example.
What did 729 have to do with LPC?
7?
On the previous slide, the DNS interface book?
Well, as I said, the RPC used the Lpc for local transportation, and there was an issue based that was exploitable through the Lpc without necessarily using directly the RPC. I didn't make much research about it. I just looked in the internet. Okay, so we made the Lpc research in order to understand really how the Lpc works, because even if it's more documented in the internet, there are still a lot of dark spots. And we really want to understand what features was available through the Lpc. We know that, for example, when you ask for some information for a specific user, if you want to change the password of a user, you will go through Lpc interface. So if there are some features that are available but should not be, that should be restricted. And of course, that's a good introduction to privilege escalation, as the Lpc help for privilege escalation. That's a lot easier using the Lpc. We thought it could be a good way to see if it needs some protection layer in the Lpc. So now I'm going to present the privilege escalation. So basically, the privilege escalation that I found was on the Lsass process. Lsass stands for Local Security Authority Subsystem Service. That's a critical component of the Windows subsystem, and it handles every request based on a user privilege and groups. It has access to the SAM database that stores all the passwords. So that's a really critical Lpc interface that has been targeted many times for local escalation. Almost all features of the Lsass process go through the LSA authentication port. And that's a really huge Lpc interface. So it implements a dispatch table. This is its dispatch table. Basically, by looking at the names, you see what is supported. For example, there is EFS for the crypt part. There is a system of packages that you can register and call. There is everything related to enumeration of user, seed, and things like that. Of course, you have also the login process. So two of the functions in the Lpc dispatch table implements a new system that I call the remote buffer system. Basically, you send a message through the Lpc interface that contains local address on the client process, and it will mirror the data in the server process. This system works with three functions. The LSAP capture buffers function will just copy your entries from the Lpc message. The map token buffer will do the mirroring. It will allocate new buffers and copy the data from the client process to the server process. And the last function, the LSAP and capture buffers, basically liberate all allocated data. So there was a mistake in the way uninstalled data was done when you use the Lpc init context function. So here is a figure that shows you every steps of the sec buffer desk, the remote buffer system. The first is the Lpc message. The second is when every entry are captured in the sec buffer desk structure. And the last step is when everything is initialized. So you can see that it changed the flag entry. So it indicates that the address is local and it should be liberated in the last function. And it changed the function for a local address. So this IDA graph shows you where the issue. Basically, you can capture the buffer, and by specifying a specified specific byte in the Alpc message, you discard the mirroring phase. So basically, you are able to submit some flag that indicates that your address you have is local, but you submit a custom address, and you are able to submit any address you want to the LTL free heap function. So exploiting the LTL free heap function is not something common, but there is many documentation about exploitation of the heap on Windows XP SP2. Basically, we used a crafted chunk in the remote mapped section in order to push a chunk in a local-side list. So a local-side list is a fast allocation list that is used for exploitation on XP SP2. So we are able to corrupt this list and return a custom pointer from the allocation, and then overwrite the part of the memory. In order to do that, we have to create a valid chunk, and the valid chunk must have a valid cookie, valid flag, and valid alignments. So the worst part is getting a valid cookie. So getting a valid cookie is basically breaking the cookie algorithm that's based on the address, a chain cookie in the heap header, and the heap cookie generated in the heap system structure, the heap process structure. In our case, the address is static, as it's in the remote mapped section. So there is only 256 possibilities. And when an invalid cookie is found, it will not break the process, it will not stop the process. So we are able to brute force this value and find the correct cookie. Basically, we have some data just after the chunk header, and we will check after every attempt if this data has been replaced by a pointer. If it has been replaced, we know it's going to be in the local-side list, and we can corrupt the list by replacing this pointer. On Lsass and XP SP2, we are on a critical system component, so the data execution prevention system is activated. This system denied execution of non-executable page, so we cannot just jump in our remote section, mapped section, because it's only mapped in read and write. So we have to find another way. Basically, we replaced an empty entry in the Alpc dispatch table, and we use that to jump through different parts of assembly in the NTDLL module, so we can get a control of the stack, deactivate the DUP, and execute our shell code. Okay, so the control flow redirection is made through the context when you call the Alpc dispatch table. Basically, we control data in the first argument in the EDI register. We do not control fully the 18 first byte of this buffer, as it is the Alpc message structure. We can look at the specific context depending on the service pack, language pack. And as I said, we get the stack control in order to deactivate the DUP and jump in the shell code. To deactivate the DUP, we use the union format technique. Basically, you jump in a part of NTDLL with a specific context that will deactivate the DUP and return on an address on your stack. So now I'm going to show you a demonstration. So basically, the demonstration is launched from a guest account, and we will corrupt the Lsass process to sniff every login attempt and reveal password in clear. So as you can see, we brute force the cookie and find the right value. Then we're able to update the local side list overwrite a part of the table and do our stuff. So now, if I'm locking my session, for example, it will create a file so we'll see the authentication workstation, the user, and the password in clear. So that it's use only a single function, and it works if every type of authentication. And of course, it works too if I try to log in with an administrator user. So that's just an example of what you are able to do by owning the Lsass process. Of course, as you are on a system component, you can inject yourself on the kernel, go in other critical components, do whatever you want. So how can we protect against this type of attack? First, we can restrict the mapped section feature of the Alpc interface. First, we thought that no one used it almost, and almost all Alpc interface allow you to map a section in a remote process, but basically almost no interface use it, support it. After some small research, we found out that some private Lpc kernel components use this feature to speed up the communication through userln and kernel. So basically, we're saying that you can have two different approaches. First, you can blacklist the remote mapping section feature on some Lpc interface that you think are critical. That's not the better way because Lpc interface evolve across versions, and you're not sure that in the version later there will not be the support of the remote mapped section feature. We can also look at the server write level and the client write level, and if the server is higher than the client, we just denied this feature. We can also disable the deactivation of the DUP. But as we saw in Windows Vista P1, there is a new function called setProcessDUP. The setProcessDUP policy. Basically, it made return to Libc exploitation even easier than previously with the uniformity technique. So that shows that deactivated the DUP protection is a feature. And we can understand that as if the DUP find out that there is an issue, it will crash the process. And if this process is a system component, it will reboot your hardware, your system. So we cannot just disable the DUP, but we can look at when the DUP is deactivated, look at the stack to see if there is some return to Libc, some kind of weird stack, and then accept the deactivation or not. This exploitation was also using the LTL free heap function. So basically, we could filter this function in order to improve the protection of the heap. When you look at Windows Vista, you see that the heap has been totally remade. It has been secured. For the moment, no one break this new security. But we cannot use the Windows Vista improvement in Windows XP 2000 or 2003 because we do not access to internal components of the heap. Basically, we're able to filter pointers for liberation or return allocated pointers, but it can slow down a lot the workstation. So now I'm going to present the Alpc. The Alpc is a new version of the Alpc interface that's been introduced in Windows Vista. The old Alpc code has been removed, but there is still support for the Alpc syscall function. If you look at the bottom figure, you can see that there is many exported functions that share the same function to respond user need. And there is some improvement in the overall performance of the Alpc if you compare with the Alpc. It supports I/O completion port, which is a thread organization system for the server. Basically, it will change the number of threads available for the server, depending on the request. And the overall performance and the user interface has been improved to respond faster and use asynchronous response by default. Is a comparison of a version in Alpc and ALPC in IDA. The top function is on Alpc, the bottom is on ALPC. The Alpc interfaces, basically, the component used a lot of big functions without dependencies across functions. If they need to check a specific flag, they will just look directly in the function and not call another function to validate the Alpc message. But in the Alpc, there is a lot more function, so the modularity has been greatly improved. There is like 20 times more crossing a module and a lot of more functions. So this new interface integrates new functions that start with the NT-Alpc. There is 21 new functions. One of the more interesting functions is NT-Alpc send wait receive port. Basically, it replaces full function in the Alpc, because before you have a function to send a message, to receive a message, to send and wait for receive a message, to receive a message and send another. So it has been a lot simplified. And there is totally new feature as you are able to open the sender thread or process, create a section or presentation, and things like that. We'll see later. Oh. Okay. Yeah. So this is this function, this new function. There is a lot of more new function, but this one is interesting. All send and receive elements are optional, so you are able to send a message or just wait for reception, or both. One of the new arguments are the message buffer. You can see in message buffer and out message buffer. So that's a new system integrates in the Alpc interface. This new message buffer system is dynamic structure. Basically, there is only two fields static on the structure. And everything related to the structure size or access to structure in the dynamic data are made using anti-DLL function. That's interesting because that's the way it managed the remote section system and in the Alpc. So in order to map a section on the remote process in the server, it's a little bit more complicated than before. First, you have to call the NT-Alpc create port section. You submit a section, or you ask the function to create the section for you. It will link your section with the Alpc per object and return you a specific handle. This handle must be set in the entry of the dynamic message buffer of the type Alpc message flag view. And this entry must be submitted to the NT-Alpc create section view function. Basically, it will initialize this structure to be ready and create another representation called a view in the kernel. Finally, you have the message buffer ready to be sent. But when you send a message buffer, it will not necessarily map the section on the server. By default, it will not, because the server has to specify in the out message buffer the type of the section view. If it's not specified, it will just not work. This architecture of message buffer is a little weird because, first of all, nothing indicates if the remote section mapping worked or not. Basically, it will show the same ways if it worked or not, and the message buffer will not be changed. Of course, you don't have the remote address like it was in XP, in the Alpc interfaces. I saw too that message buffer is available during the connection, but as a message buffer is linked most of the time with an Alpc object, and the Alpc object does not exist for the connection, I don't really understand how it works. Well, there is another way enough that when you map a section, then disconnect from the Alpc and redo every steps to remap this section on the remote process, the section will be mapped twice, and you can do that whatever you want. So basically, you can fill the overall system with your section. Basically, that's like ape spray attack without the ape. That could resolve the issue of that you don't know the base address of the remote section. But as I said, most interfaces, Alpc interface does not support the section mapping. So the vulnerability was in a new component called a resource reserve. This new component basically is around a type that is linked with the Alpc object called a blob type. So the blob type resource reserved basically link an empty kernel message object with the Alpc object. This message, this presentation of a message in the kernel, is not linked with any Alpc port or any process. That's a blank message. But we're not sure exactly what it is for because we don't see any world example. It is not used by any interface. And I even think that Microsoft did not know if they use it or not. So here's the vulnerable assembly. First, it will look up for a message from the message ID. If you submit a sign-in message ID, it will look for a resource reserve, a message linked to a resource reserve. And later, it will try to access the Alpc server object. But a resource reserved message does not have a link with the Alpc server object. So basically, it will try to access null. In Windows, you are able to allocate the null page. Then we're able to redirect the data that will be used. And finally, it will submit a pointer from the Alpc server object to the exafquery post-lock shared function. That's a lock mechanism function. So we're able to change the behavior of the process and overwrite a single byte in the kernel. In order to allocate the null page, you have to call the anti-allocate virtual memory function by specifying an address in the first page. It will allocate the null page. I think there is another way to do that, but basically everyone uses this way. So we must target something really special, as the exafquery post-lock shared is an undocumented function, and it's a little bit complicated. So basically, we made some tests to see how it will change data when it acquires an address, and when you erase it, we saw that when the high byte is set, it will set the low byte to 1. It only works in Vista because on XP and other versions, it does not behave the same way. We target the blob definition structure. That's a structure in the data of the kernel. and basically it defines what is this blob type entry by an ID and some callback function. You can see that the dealt callback function is null. You can set up a null callback, it will not be called, but using the next pointer and align this pointer, we're able to set the height byte, and then we will set the low byte in the null pointer. That's a little bit. There is more details in the paper that explain every steps what is done when you acquire the pointer, they acquire the lock, when you release it. I show you a demonstration, so it will be a little more clear. So for this exploit, I made a breakpoint to show you the stack. So if you look at the stack, you see that we call a syscall. That's why you have the KI fast call entry. And then the stack is in the kernel, and it will call the userland. That's how we get the execution of the userland code in the ring 0 process privilege write level. I said that on the line you set the low byte to 1, and that's why it called the 100 function in hexadecimal form. So this exploit just changed the parent process token in order to increase the privilege of the caller. You can see that first we were a guest called a mix, and then we are a system. Okay, so basically the kernel is now the next exploitation landscape, because exploiting the kernel is a lot easier than exploiting userland, especially on Windows Vista, where every system component code base has been drastically improved. The previous vulnerability was not exploitable in Windows Vista, not only because the app changed, but also because they changed the Lsass system. They improved the code base. In the kernel exploitation, a null difference is is as important and even more stable than a simple overflow in the app or things like that. But as you have to protect the kernel, the protection will be a lot harder than for userland, because if you made a mistake, you deal with undocumented stuff, and if you made a mistake, it will crash the overall system. So for a third-party vendor, it's not acceptable. Basically, there is two approaches. First, the software protection. You see, you look at common actor attack vector, and you modify the operating system behavior to deny, for example, the null page allocation. As before, we thought that the system does not use it, and we were wrong, because it is used like for video initialization, or everything related to thread creation on the kernel and in the userland, and maybe some packers can use it to hide themselves. We can also add the kernel pool. The kernel pool is the heap of the kernel, and it is used a lot during exploitation of the kernel. There is a paper from Kostya Koshinsky about that during SysCon Hong Kong that's really interesting. It's possible, but it needs a lot of reverse because it uses a lot internal structure unexploited by the kernel. The other approach is using the hardware in order to restrict the operating system. We can use the virtualization as for rootkits, but basically we can talk about it, but it's a lot easier to talk about it than create it. So it takes a lot of time, and you have to be really careful, because the more you monitor the system, the hardware, the more your system will slow down. That's certainly the best choice to protect the operating system, but that's also the hardest. PAX integrates a component called kernexec that's not really known. Basically, kernexec creates a separation between the userland and the kernelland. The userland is accessible only when the Linux kernel calls a specific function called getUser. So it restricts basic kernel escalation, as userland is not available. It's not the better restriction, but that's a good way. But it's not possible on Windows because the Windows kernel protects itself, but does not protect others. It does not use a single function to access the userland. There is also concept like protecting the EDT, the syscall table, the GDT that are not applicable in Windows because all antivirus and third software hook those tables. So the conclusion, of course, there's still vulnerability in the Windows subsystem components. Most are unusual. Windows Vista improved a lot its code base and robustness. We saw a Windows Vista pull execution directly in the kernel component, the main kernel component, but the main kernel component is certainly the more secure in the kernel address space. There is a lot of other drivers that are easier to attack and to exploit. I believe that serious kernel protection will need an improvement in the way the Windows kernel is designed, because for the moment you are between documented stuff and undocumented stuff. You have to go far in the undocumented stuff to create a good protection, but basically when you do that, you can create some issue on the operating system, some unknown behavior, and that made the development even harder. So thank you for your attention. Do you have any question?